All right, we're continuing on in Windows kernel world. Today we're with Jon Berry, and we're going to talk about connected standby and other very interesting things that are definitely related to power management in Windows 8. So tell us a little bit about yourself.
Well, I started at Microsoft a little over 20 years ago, straight out of college.
Wow.
For the first 12 years or so, I was on various incarnations of the shell, or user interface team. Initially on what was called Cairo, which was a long time ago, and various parts of that team delivered the Chicago shell that became Windows 95, and then we did NT4, where we took that code base back instead of the other stuff we've been working on. And so I was a dev lead, dev manager. I was dev manager for the shell for Windows 2000 and Windows XP. I spent a couple of years doing legal special projects that were technical, but very much away from what was going on, which was Alpha Longhorn. When I came back to the product team, I switched over to help the IE team, which was sort of staffing up again after a period of lower staffing and less focus. So I helped IE get back into the game of shipping out a band again and being on the current code base, and then I got flipped back from being an IC to dev manager. So I was dev manager for IE7 and the beginning of IE8, and then I was a dev lead for IE8 and part of IE9. So did lots of internal plumbing kind of stuff, you know, multi-process model for IE8, and then completely differently, the HTML5 canvas tag for IE9.
Wow.
So that was fun and interesting.
Absolutely.
Very different. And then I switched over to the fundamentals team, where I am now, and ended up working on performance, but mostly power. How to make sure that these new classes of devices could have competitive, super long battery life. So that kind of leads us to connected standby and the Desktop Activity Moderator, which is the component that I'm going to mostly be talking about.
Okay.
But first, I kind of have to set the context. With Windows 8, we are enabling a new class of hardware. These are, up to now, entirely based on system-on-chip designs. You know, there are ARM versions, there are Intel versions. These new classes of hardware allow such a low power floor that you can implement a power model that is much more like a smartphone, rather than the sort of typical PC power model, which has been, when you're on, there's multiple states, multiple frequencies, but when you're off, it's generally some flavor of, S3 standby, sleep, or S4, which is hibernate, I persist to disk instead of just persisting in memory, and of course, off. Well, with the new classes of devices, these connected standby, as we call it, capable devices, it allows a class of always on, always connected. That's the catchphrase we use for these scenarios where, for example, you've got your device, it seems to be off, it can be sitting on your coffee table for days long. It is in an extremely low power state, so it's not draining battery very fast, and yet when you turn the device on, your email is current, your instant messages are there, things that you would like to have been kept in sync in the background are there, fresh. It's got, your latest news feeds. It's fresh. So this is sort of a key building block of Windows 8. So, of course, Windows 8 still supports all the existing hardware too. that stuff still works just as well as it ever did before. And in fact, the work we did to be particularly power efficient on these new connected standby capable devices, of course, pays dividends on the existing, sort of legacy power model machines as well. In fact, we've got articles posted on the walls out here in the hallway, even from our, beta and sort of preview releases, where people say, hey, I took my old laptop and I installed the Windows 8 release preview and I got a half an hour more battery life on something that, previously only did 3 or 4 hours. That's a tremendous accomplishment to eke that much more battery life out of a device that might be 3, 4, 5 years old. Like that's something that, like a lot of other things, it breathes new life into existing hardware, which is great. It's something that's compelling to customers, independent of all the other new features that we've added to the product.
So that brings the question, of course, when we talk Bruce Worthington, people have probably seen that video by now, or will see it soon, which is focused primarily on power. But you guys actually had to write more power efficient code. So is it that surprising that current hardware would also be using less battery if you're not always waking up to pull things and you're not, do you know what I mean?
No, not surprising. I mean, the tactics that we used and the techniques were, in many cases, there was no rocket science to them. There was a will to do what we knew we should do. Like there was a greater will to do it in this release. There was more motivation because we knew we had these lightweight, small battery devices that had to have compelling battery life. So I say not rocket science. I'm talking about removing wakes from the system. With any kind of processor that does even minimal power management, if you're waking the processor up frequently, even to do very little bits of work, there's a cost associated with waking up and then going back down. That cost doesn't get amortized over enough time to pay it back. So if you can reduce the work you do, obviously that helps. But even if you're doing the same amount of work, if you can consolidate things together, then you end up having longer stretches at the lower power state, and the payback on that kind of work is disproportionately good. If you reduce the amount of time where you're having any kind of wakes, you can see sort of outsized return on investment. So now that said, Bruce and his team did actually do some stuff that was rocket science, but that's for him to talk about, not me. So, new class of hardware, capable of this connected standby mode. I'm going to sketch out basically a kind of a flow, like from when the machine is from awake going into connected standby. So this will help to visualize, and then we can kind of show you where the DAM, the Desktop Activity Moderator, fits in.
Excellent.
So let's see. I'm going to just draw it as a series of boxes. This is entering connected standby. So at the beginning, this is the scenario where the user hits the button on the Slate device. Screen goes off very fast, less than 300 milliseconds. It's got to be, feel like instant responsive. So at the very beginning here, we can say, screen off, and of course, the screen is also a digitizer. It's detecting touch input, so basically we'll say various forms of input, like the digitizer and the screen, go off. Then there's a check for remote sessions. So because these Windows 8 devices are full PCs running a full operating system, you could have a remote session where you're connected to this device from another PC. If that's the case, we don't want to go any further down and start suspending and freezing things on the device because the remote session might be actually using it. So if there was a remote session, which is obviously not the common case, we would stop right there. But typically, if you don't have a remote session, then we go into Process Lifetime Manager phase. Process Lifetime Manager is the component in the system that manages the life cycle of these modern Windows Store applications. They are new for Windows 8. They have a highly regulated life cycle. Like, it's very obvious when they're in the foreground, when they're in the background. When they're in the background, they get like 5 seconds to suspend themselves, persist their state. After that, they might be terminated or they might be brought back. But apart from a very well-defined interface by which they can register certain background tasks, they're generally only running when they're in the foreground, when they're visible on the screen. So typically, and you can do snapped and docked two Windows Store apps on the screen at a time.
Mm-hmm.
But for simplicity, we'll just consider there's basically only going to be one or two of these guys that are in the foreground at any given time. So the component that is helping to arbitrate this whole sequence of things is called the PDC, the Power Dependency Coordinator, not Primary Domain Controller. Sorry for the overlap of acronyms, but the PDC, he's the traffic cop who's saying when it's okay to move from one state to the next. Do this stuff. Check this guy. Okay, no remote sessions? Now, he tells PLM, up in the shell, quiesce your constituents. So he goes up, talks to Explorer. Explorer says, okay, you app, suspend, boom. Okay, you're done suspending, great. Comes back here, PLM tells the PDC, okay, my guys are done. Then we move on to dam phase. Now, dam phase is for desktop applications. The thing that is interesting about this is, hey, Windows 8, running a full operating system, running a full version of Windows. On Intel-based machines, that means you have the entire wealth of Win32 applications that you can run on the system. That's a tremendous advantage, in being able to use all this existing software. But a great number of those existing applications weren't designed to be particularly power savvy. They aren't like smartphone applications that, were required to think about that kind of stuff right from the get-go. So we have a lot of desktop applications that are badly behaved. And it's not because they're poorly written. We've got lots of really good applications that do things that, when you look at them from the power perspective, are quite unfortunate. You can have an application that has some kind of, background task loop that is saying, oh, well, there's no user input, but maybe I should be looking for, doing some tasks in the background. Oh, I could be repaginating or something like that. And they might have a timer that fires, every 100 milliseconds or less. So something like that means if you just have that application up, sitting there, it seems like it's quiescent, but in fact, it's waking up the processor 10 or 20 times per second. Each one of those little things is very cheap, but it means that we don't get any nice long periods where the processor gets to go down to the really efficient state. So in order to deal with that, we had to do something. Otherwise, all the desktop applications, especially on Intel, where there's a huge wealth of these desktop applications, would never be able to have great battery life. So, thus we have Desktop Activity Moderator, a component whose job it is to make sure that those guys quiet down. Now, with the modern Windows Store applications, there's a well-defined interface where they get told, okay, now's your time to run, okay, now it's time for you to be quiet. With desktop applications, there is no such thing. We can't set the Wayback Machine, go back 20 years, and change how everybody wrote all those great applications. So we have to retrofit the behavior from the outside. And this is where the minor grade rocket science comes in.
Sure.
Okay, we would like to basically freeze these guys. Oh, well, freezing these guys is, well, we do have mechanisms. We could, like, suspend all the threads, but wait a minute, we can't actually do, like, the fine-grained suspension like the PLM does. See, with the modern Windows Store apps, they're all running in app containers. There's a large degree of isolation between each individual application already. They don't reach over and talk to each other. They don't have a whole lot of, I'm going to have a named mutex and I'm going to share it with this guy over here. No. They're in an app container. They all got their own copy of base named objects. They are living in a little bubble, and that is by design. With desktop applications, there are almost no end of ways that one application could be implicitly relying on behavior and activity from another process way over here. Everybody shares the file system, everybody shares base named objects. It's very easy for there to be dependencies. And it would be almost impossible for us to tease apart those kind of dependencies and do the fine-grained, okay, I'm going to suspend Adobe Lightroom, but I'm not going to suspend Microsoft Word, and I am going to suspend, Adobe Flash Player, but not Quicken, and, bad juju.
Yeah.
So, basically, what it came down to was the only safe way to do that is to make sure that they all get frozen as a unit. And this largely obviates the concern of dependencies between applications, because they basically all get flash frozen together. So it's to the application as if the machine went into S3 or S4, the existing kind of sleep and standby or hibernate states. And in order to guard against there being dependencies from these guys onto these guys, even though there really shouldn't be, we only do this freezing thing when the screen goes off and when we enter connected standby. Technically, you're entering connected standby as soon as the screen goes off. There's just sort of different states and levels within connected standby of, further and further suppressed activity. By being very, very careful about when we apply this thing and how we do it, we can do something that otherwise would seem crazy from an AppCompat point of view relatively safely. So we only do it when the screen is off,
okay.
And therefore by definition there's no user input going on. The digitizer is already off, there's no touch input going on, there's no mouse or keyboard by definition. So you really can't be relying on a response because you haven't given it any input. And we do everything as a unit so that dependencies between the things don't end up being deadlocks. That's the simple version.
Okay.
The implementation is a little interesting because we have things like protected processes that can't be hooked and are very resistant for good reasons to external manipulation. We have interesting sort of implementation details, which I can give you some information on. The way we ended up implementing this is to make it a kernel extension. It's a driver.
Okay.
It doesn't actually handle the device. But it's running in kernel mode. in part to handle those protected processes that I just mentioned. It's hooked in very, very early in the process creation path, almost like an antivirus, like a program would be.
Okay.
It looks at each process before it gets created, before it ever transitions into user mode for the first time. The DAM makes a decision like, okay, what category of process are you? Are you something that should be exempt? Are you something that should be frozen? Or are you something that should be throttled, which is kind of in between? Throttle is actually something we only use in the session 0 for like services and other tasks and things like that run in session 0. We base our decisions on what the process is. It's the policy is actually implicit in the binary, and we tried very hard to make sure that all of our mechanisms were not abusable by either malware or by somebody who thought, oh well, I'm special, I need to be running all the time. No, we have great mechanisms for you to be running at the appropriate times. We have maintenance mode, we have modern apps, we have all these kinds of things. Those are the right ways to be running at the appropriate time. Don't be a shell, startup group thing that starts up and runs all the time and just does nothing except, drain the user's battery 99% of its lifetime. So, dam.sys puts each job when it gets created puts each process into a job object.
Okay.
That's the underlying mechanism that it uses for, bookkeeping, if you will. Now, people watching this video will probably say, but wait, job objects, if I'm already in a job, I can't be put in another job. Yes, that was true up until Windows 8. But in Windows 8, the kernel team added the ability to nest job objects, which was essential for this, as well as another component called the PSM, Process State Manager. It's the guy underneath the PLM who actually does a very analogous thing to the DAM for the Windows Store apps.
Okay.
He also uses job objects and freezes and thaws things, although PSM does it in a much more fine-grained way, sort of at the individual package granularity, whereas I do things at a much coarser grain, basically per session granularity.
Okay.
So, job objects cannot be nested. So, if you are an application that uses job objects yourself, then it's no problem. You will already be in a job object when your process gets created, but you can go ahead and create your own jobs, and you should be blissfully unaware that anything has changed because everything will just keep working for you. The other, other thing that might be interesting, how we actually freeze things. So we tend to use suspend and freeze kind of interchangeably, but while the mechanism is the same if you get far enough down in the kernel, they're slightly different until you get quite far down. Suspend counts, people should probably be familiar with already. You can create a thread, suspend it, and then resume it later after you've poked information into it. The suspend count is something that's kept per thread, and it's something that the application can actually modify. Win32 apps at least they can increment and decrement the suspend count. Freeze count is something that only the operating system can manipulate. It's like, for example, the mechanism that is used when you are broken into the debugger.
Okay.
That's freeze count, incrementing and decrementing. So by using the freeze count and enhancing the functionality of that, again, both for the PSM and for the DAM, we're able to reliably freeze and thaw whole packages or whole sessions at a time in a way that is guaranteed not to freeze at a bad time, say, in kernel mode while some lock is held or something like that. And also reliably, you can't, for example, have a process that is desperately trying to create new threads or child processes or something like that, and therefore escape getting frozen. We've covered over all those potential holes, so that things are nice and reliable. And because the freeze count is independent from the suspend count, if you were in the middle of manipulating suspend counts in your own process, when we freeze you and you come back to thawed, everything is exactly as was before. It's all reference counted. Again, by not using the suspend count, we don't have to. We avoid a whole class of potential app-compat issues.
Okay.
So the DAM actually does two things in the system. So now I'm going to go on to deeper states of connected standby and talk about the other thing it does, which is throttling the session 0 services.
Okay.
So PLM phase, DAM phase. At this point, your modern Windows Store apps are all suspended unless they've got background tasks going. Audio or the thing that can process incoming mail, that kind of stuff. All your interactive session desktop apps are now frozen. Now, I'm going to abbreviate. Low power epoch. From here down, it's progressively more and more strictures being put into place to suppress more and more kinds of activity. The last thing over here is it's called resiliency. And when you get down into resiliency phase, there's some interesting stuff that happens almost completely under the covers, but people might be interested in knowing about it.
Yes.
I'm going to pull back here. So there's some. I'm going to use abbreviations, but I'll talk through them. Network quiet mode. There's DAM resiliency, which is the session 0 stuff. There's I/O coalescing, and then finally idle resiliency. So these are the 4 mechanisms that we use in Windows 8. Network quiet mode is very important to getting to the lowest possible power state. It says that when you aren't using the network, we are going to actually have it power down. It goes into a low power state, at the device driver level. I talked about how wakes are so insidious to getting to and staying at a low power floor. If you're on a wireless network, just the traffic, coming within your local network could be enough to keep your machine in a state of, caffeine high, just because every time a packet comes to your network card, he's going to generate an interrupt. Hey, I got something for you. Oh, you didn't care. Hey, I got something for you. Oh, you didn't care. Most of the time, you don't care.
Yeah.
Well, I had to do something there. So they did some very nice work, both in the firmware and in the software for the networking componentry, to say, we're going to program the firmware to filter incoming packets. We're going to say, you're familiar with the Wake on LAN, the magic packet that you can use to send out to your enterprise. Wake up that desktop, tell them to download some patches, something like that. This is sort of like the generalization of that mechanism.
Okay.
I'm going to have a series of wake patterns programmed into the card, such that only if you match one of those wake patterns, like it's to my specific address and it's coming to this port, and certain criteria must be met, only if those conditions are met does the network driver actually say, okay, now I'm going to generate an interrupt, wake up the CPU, and have him say, oh, okay, packet for me, great. I've already got my modern mail application pending. I'm going to unfreeze him. This is PSM. I'm going to unfreeze him. He's already got a read hanging for that input. Boom, he gets it. He downloads his latest email or it's Skype, getting an incoming phone call or something like that. Now, basically you went from here jumped back to an earlier stage, played a tone, popped a toast, did something like that. User says, oh, incoming call, hit the button, boom, screen on, now you're back here. And getting from here all the way back here is a fraction of a second. It's very fast. So, in the resiliency phase, basically telling the network to go quiet and dark is a very important one. It's basically the first thing we do. Then we start throttling stuff in session 0, which enforces nice, long, quiet periods in between wakes. Again, the reason we can get away with that is because, by definition, screen's off, no user input. Hey, if things are delayed a few seconds, if a tree falls in the forest and nobody's there to hear it, Now, we had to be very, very careful that when background tasks were running, that these mechanisms wouldn't interfere with their processing, because some of that stuff is time critical. If you get an incoming IM, or especially an incoming VoIP call, even a second or two delay is unacceptable, because you need to answer the phone before the caller hangs up.
Yeah.
So there's a nice architecture within here whereby system components that know about all the background task scenarios ensure that these mechanisms are disengaged whenever the relevant kind of background task is executing. So that's what guarantees that, oh, when I need the network will be up. When I need a timely response and I can't afford to be delayed on some disk activity, session 0 throttling and IO coalescing, they'll be disabled. Last one is idle resiliency, which is basically forced timer stretching.
Okay.
It's kind of two things. On the one hand, if nobody has asked for a timer in the next yay long, then we will ensure that the timer interrupt doesn't fire until the next time it really needs. Be lazy. Lazy is good. And furthermore, if you ask for, it enforces a minimum period. And if you ask for a timer, hey, I want to be woken up in 5 seconds, you might actually get woken up in 30 seconds.
Okay.
Because that really helps keep the machine into the lowest power state. And they did a lot of testing, a lot of work to figure out basically how far they could push it before things started to get flaky and backed off. And so we have a system now that is sort of very carefully orchestrated to keep the machine as quiet as possible, but no quieter.
Okay. Keep it alive.
Yeah. We enable these interesting background scenarios by making sure that whenever anybody is about to do something, that before they ever get to that point, we've woken up the appropriate resources, and hopefully minimal, but we've woken up all the resources they would need in order to do their thing. So this is not the kind of thing that an app writer needs to know, because by and large, it just works. And even background task authors generally don't need to know about this kind of stuff, because we have done the work to make sure that it just works. But I think it's interesting.
Definitely interesting.
It's a nice model. I was very happy with the way it worked out. And so now you see, getting back to, how does the DAM fit in all this stuff? But the DAM wears two hats. He's freezing all of the session 0 or session 1 and session 2 kind of stuff. You could even have multiple users logged in on a Windows 8 slate, which is great. And he's also doing this stuff under the covers, which is, well, actually, I hope the whole thing is under the covers. I kind of describe this as, it's plumbing. Plumbing can be fun. Plumbing can be good. Plumbing is valuable. But it's sort of like what I imagine working for the post office or an electrical utility is like. You do your job great, nobody notices you. The only time you ever get attention is when something's gone wrong, and so basically any attention is bad. So I hope everyone who's watching this video that you never have to care about my driver because it never got in your way. It just let you have surprisingly good battery life on your Windows 8 device.
Excellent. Very nice. So, what I would like to ask is, using, say, Office as an example, Outlook, just got to check your mail. It's got to always pull out to the internet to make sure that check and see if you have mail or not. So, one of the things that I'm curious about is, I know you guys did some work with thread priority. Like, I'm very important. I'm really important. This thread is critical. I need to check email. So, what I want to ask you about is when I get into that state where I'm done, I press the little button and it goes black. What exactly happens to an application like Outlook that's running in desktop mode? I know you sort of briefly touched on it. What exactly happens? I mean, when you say freeze, is it a dump file? You want to know its state, right?
No, it's not a dump. The process is still alive. It is still in memory.
It's still in memory.
Yeah, but what happens is that for each individual thread, there's an APC queued to it that says, increment your freeze count. When a thread is in kernel mode and might have some locks, could be in critical regions or something like that, APCs won't fire. You're at DPC or higher, or you're in guarded regions, that kind of thing. Basically, when the IRQL level drops down enough that an APC can be processed, then the system knows that it's safe to increment the freeze count. Oh, freeze count non-zero, I will not be scheduled. So that's really all it means under the covers.
Okay.
When you freeze a process, it just means that you've marked each one of its threads so that those threads won't be scheduled when the processor is deciding what to do next.
Okay.
And then the inverse when they come back.
Absolutely. We'll go and run everything.
So, I guess I should have said, at the beginning of this project, I proposed that we should create a component that did this kind of thing. And initially there was skepticism, or at least, a healthy fear that this might be bad for app compat. Can apps handle being suspended and resumed or frozen and thawed, a lot, or at inopportune times or something like that? What's going to happen? So the good thing was I had access to our whole app compat team here in Windows, who already had ginormous, automation suites of literally thousands of Win32 applications that they put through their paces with, every build of Windows. So I was able to go to them with a prototype that did something far more stressful than the actual implementation did, and said, okay, do your worst. Put this thing on the machine and then run through your whole app compat verification suite. And the results were spectacularly good. And that gave people a lot of confidence that, in general, applications can be frozen and resumed just fine.
Great.
It's not something that causes them to freak out. And there were, it just made me think of another thing. There were other things that we did to try to make this as seamless as possible. I mean, really the only difference between this sort of virtual S3 mode that the desktop apps go into and you're in connected standby compared to a real S3 on your laptop is that some components low in the system are still running. So there's an asynchrony, something's frozen, something's running, that doesn't exist on a machine in S3 where everybody's frozen together, in toto. So Arun Kishan, who you've heard of, he's
been on
he's famous.
He's famous.
He had done some work that I was able to leverage for this component that was, I guess I call it timer relativizing. He calls it timer virtualization. Basically, if you set a relative timer, before his changes, if that timer would have expired while you were frozen, then the system would have had to wake up under the covers, look, see, oh yeah, but he's frozen now, so never mind, and then, you know, deliver it like after the resume, which meant there was this whole stampede of activity on like resume from hibernate or resume from standby. The change makes those things sort of relative to uptime rather than wall time, if you will. So I'm an application. I schedule a relative timer for 15 seconds from now. 5 seconds later, the machine goes into connected standby. When I'm resumed, 48 hours later, my timer still fires 10 seconds later. That helps with a variety of, you know, sort of timing sensitive applications.
Absolutely.
And furthermore, the mechanisms that you can watch for to know that you're about to be, you know, go down, WM Power Broadcast, you can actually opt into getting those kind of notifications too, if you really care. Like if you are like a desktop audio playback kind of a thing, you can say, yeah, I want to know if I'm about to be frozen, so I'll pause audio playback or something like that. Now, maybe that's not such an important example. You know, media players is one where there's already a bunch of good options, and the Win8, you know, in the box and in the store. So I don't know how many people are going to be playing their desktop media player, but if you did, it can still do a nice job. There's relatively little dislocation on Win8 for those kind of things, even on these connected standby capable machines. So, I mean, in general, we tried to be as good as possible on AppCompat while still delivering the really compelling battery life. We had to make, you know, trade-offs all the way through, but in the end, I'm pretty happy with what we ended up.
Absolutely. Now, one of the things that, well, the last question I'd like to ask, I mean, from now we've gone way down to come back up a little bit, and one of the things that I think is abundantly clear when you're using Windows 8 is, let's say you're playing a game, a Metro game. I said Metro, sorry. A modern Windows Store app game. Forgive me. You are right in the game, you're shooting at things, you're blowing things up, and then you hit the Windows key or you hit the Windows D key and go to the desktop to check that oh so important email. And then you come back and there you are exactly where you were, everything's happening, music and whatnot. That is a suspended state because you're leaving that environment. Is there a relationship between, is it sort of a DAM light or a connected state light or connected mode light? Do you understand what I'm asking?
The mechanism underneath, you know, like I said, the PLM uses a lower level component, PSM, to do. It's the one who keeps the jobs for the modern object for the modern you know, Windows Store apps. It uses the freeze thaw, the nested. Well, actually, they don't have to do nested jobs, but you know, all the basically, I worked with Arun extensively to make sure that all the mechanisms that he added in order to support the modern apps could also be used just as well for the desktop apps. And in the end, that worked out very well. You know, in that particular case, you switch away from the you know, your shooter or something like that. They're probably going to pause the game as soon as they get the not visible notification, which is even quicker than the hey, please suspend yourself. You know, because they want to be quite, you know, obviously. If you're in the middle of a first-person shooter, you can't afford to have, you know, 2 or 3 seconds of, well, I switched away, and oh, I got shot, and oh, I went back, and man, I'm fragged, so whatever.
Yeah.
So of course, you know, I think that's why they made sure that we had a, you know, not visible. But there's a little bit of when you switch away, they have to do the right thing as far as timing of like, okay, how quickly are you suspended, and then basically if you switch back to it before you even finish suspending, can you still be responsive and that kind of stuff. That's
amazing. Yeah.
That's kind of a different area.
Absolutely. I mean, that's their way up. It's further up the stack.
Sure.
Right on. Well, this is great. I mean, this is all about learning what's happened. Windows 8 is the next version of Windows. It's actually an evolutionary step in our general purpose operating system. So it's nice to know what it took underneath to enable what we see up above. So this is wonderful, great work, and I'm really looking forward to playing around with some of these new devices and putting them in standby. We'll know exactly what happens. Right on. So nice to meet you, John.
Thank you.